Alright, section 1.8 is on page 63, talks about introduction to linear transformation. Transformation is really, I'll show you a couple of examples how to transform one image into another. Linear is a special type of transformation. So, AX equal B is a transformation. You're taking matrix A, multiplying that by vector X, and you're getting a vector. So, if you multiply by AX equal B, this could be a transformation from R4 to R2. 4 dimensions to 2 dimensions. Linear transformation is going to be noted by T. And it's going to be T of X equal, and they have to specify what their transformation is. And this is Tx, and they write it as Tx. Here you're mapping from Rn to Rn. So the dimensions are not always the same, and I'll point that out as I do a couple of examples. We have some graphical examples which will explain this. So for now, this specific map right here, if I look at this problem, number 2 on page 69, given matrix A, given vector V, U given vector V, it says define the transformation from R3 right there to R3 right there. No biggie. That transformation is defined by simply taking matrix A and multiplying it by whatever that vector is. When they say find T of U, well, according to this, whatever goes in here, you simply multiply A by it. That's really what it is. And what's A? A is the vector a half, 0, 0, 0, 1 half, 0, and 0, 0, 1 half. It's a diagonal matrix with all the diagonal entries being a half. If you multiply those out, what you would get is, so this is 3 by 3, and this is 3 by 1. You'll get a 3 by 1 of 1 half, 1 half. I'm sorry. You'll get 1 half, a 0, and a negative 2. So what does this mean? Let me show you graphically what that means. You took the vector U, which is 1, 0, negative 4. I don't know why I extended it that long here. Let me do it again. And let me give it some space because I need 2 of those. There's 1. And we're mapping still R3 to R3, so we're still in the same dimensions. So here I'm taking the original, which is 1, 0, negative 4. So this is actually vector U. And it's being mapped into 1. So it's really 1 half, 0, negative 2. That's really T of U. That's what it's doing. It's shrinking it by a factor of 2. Obviously, it's right there. You can tell, right? And if I would like to look at T of V, well, again, that's going to be 1 half, 0, 0, 0, 1 half, 0, 0, 0, 1 half. So all what this does is shrink any vector by a factor of 2, nothing more. Oh, that's a C, isn't it? That's all what this vector does. So kind of like this is when you take your phone out. Remember your phone has a rectangular array, and you zoom in or out. You know when you zoom it says times 2, times 3, times 4, or zoom out 0.5, something like that. I'm looking at number 4. I'm trying to read it and understand it. It says, this transformation is simply AX. Find X, find this X, whose image under T is B image. So how do we work? AX, that's in the domain, equals B. That's the image right there. And that's the pre-image, right? So transformation, AX equal B. There's X, you take A, apply it on X, and you end up with B. This is the image, and this is the pre-image. This is domain, and this is range. Range is the image. Same with the T. So, they're saying here, determine whether X is unique. What are they saying? They're saying AX, well, there's A, X equal B. Determine X. Does that sound familiar? I could write it for you. If I write AX X equals B. There's A, there's X, there's B. What do they want? They want us to find X. Hey, does that look familiar? Yeah, we just did that. We really know how to do this. Do we not find the solution? Well, yeah, we'd use Gaussian elimination, and what I did that, what I got was, on number 4, I got a 1, 0, 0, negative 5. I got a 0, 1, 0, negative 3, and I got a 0, 0, 1, and a 1. What does that mean? That tells me that X is actually negative 5, negative 3, and 1, and this is a unique solution. That's all they're asking. So all what you have to do is read all of these terms and map them to what you already know. Get it? Map them, like transformation, the actual map. And the same with number 6. Well, they give us that. Well, we could jump straight to it, right? We could say, you know what? This is going to mean we're looking at 1, negative 2, 1, and a 1, 9, 3, and a negative 6, 3, 0, and negative 3, negative 4, 1, and a 5, 5, 1, and a negative 4. And if I map this and work it out, what I end up with is a 1, 0, 3, and a 7, a 0, 1, 1, and a 3, a 0, 0, 0, and a 0, a 0, 0, 0, and a 0. So, they were asking if X is unique here. Aren't you going to say, again, look at the pivots, right? That's 1, that's 1, so that doesn't count. I only have 3 unknowns. They gave me an extra equation, so what? So that means x3 is 3, and x2 is 3 minus x3, and x1 is 7 minus 3x3. So basically the solution is really 730 plus x3 times negative 3, negative 1, and 1. You really want to start writing the answer this way. This is not unique. And why is that? Well, because if x3 equals 0, I will get 7, 3, and 0. But if x3 equal 1, I will get 4, 2, and 1. So there are an infinite amount of solutions, which means it's not unique. And if it's unique, that means one thing, and if it's not unique, that's a totally different thing. Don't mix those. Let's see if we understand what this is saying. This problem right here says, in 9 and 10, find all x. Find x. In R4, well, that's because we have 4 of those, x1, x2, x3, x4, that are mapped into the 0 vector. By the transformation, x is mapped into ax. What does that mean? Mapped into the 0 vector. That means pretty much what you think. I hope you think what I'm thinking. That means a times x equals 0. Find x. So how do we do this? Well, we just put 0, 0, 0, 0, and we work that out, no? We did this already. And if I do this, if I work this out, I will get 1, 0, 3, 0, 0, 0, 1, 2, 0, 0, 0, 0, 0, 1, 0, and a bunch of zeros. That means x is actually, so x3, that's a 0. Again, look at the pivots to figure it out. Whatever you learn in one section, it applies to all of them. So doesn't this mean that this actually apply to x3? X3 is free. x3 is free. This is always 0. That is negative 2x3. And that is negative 3x3. So, of course, this is not unique. Right? They're not asking for that. They're saying find all the vectors. Here they are. What's x? 3. Any value you like. And you'll notice number 12 refers back to number 10. Looking at number 12, this is what it says. It says let B be the following vector and A be as it is in number 10. Here it is. It's asking, is B in the range of the linear transform? What does that mean? In the range. That's what it's asking. What does that mean? That means I need to solve this system. That means if I copy A down, 1, 3, 9, 2, 1, 0, negative 2, 0, 1, 3, 3, 2, 0, negative 4, 3, 5. And instead of being the zeros, that's B right there. And I'm trying to see if I can find the weights. And if I do this, I would really get 1, 3, 9, 2, negative 1. I will get a 1, 2, 3, negative 1. A 3 and a 0, a 17 and a 1. Doesn't that say 0x4 equals 17? 0 cannot equal 17. There's no solution. What does that mean? B is not in the range B is not in the range of the transformation, of the linear transformation. Of x being mapped into AX. And here we're going to graph those a bit. This is going to be a bit of fun, just a bit. It says in extra 1316, use rectangular coordinates system to plot if I plot this vector 5, 2, 1, 2, 3, 4, 5, 1, 2. This is vector u. Right? And v is at negative 1, negative 2, 1, 2, 3, 4. There's vector v. If I take, so it says, use rectangular to plot those, I did, and their images under the transformation t, there's t. Describe geometrically what t does. Okay, well, let's see how this works. If I take a half, 0, 0, a half, multiplied by 5, 2, what do I get? 2 by 1. 5 halves times 1 is 5 halves, plus 0, that's 0, and that's a 1. So what does that do to u? It'll take u and it'll map it into 1, 2.5, 1. And what does that do to v? If I take t of v, I forgot to write that, t of u. That would be, again, a half, 0, 0, 1 half, multiplied by negative 2, 4. That will yield negative 1 and a 2. Negative 1, 1, 2. There it is. And if I want to do the same to 16, what 16 does, 16, let me use a different color. Let's use blue. So if I take t of u, that would be 0, 1, 1, 0. Applied onto 5, that's 0, 2, 5, 0. So the point, the vector 5, 2, it will be at 1, 2, 1, 2, 3, 4, 5. And if I apply this on vector v, you know what, let me make another graph. So in this case, what happens, it took 5, 1, 2, 3, so there. And when I applied it to v, that is 1 half, 0, 0, 1 half, applied on negative 2, 4, and that would be, no, wrong one, right? 0, 1, 1, 0, that will be 0, that's a 4, negative 2. So negative 4, 2, 1, 2, 3, 4, negative 1, negative 2. That's the map. And if you look closely, this is a reflection, and the other shrinking it by 2 and reversing the order. You just need to see it geometrically. We don't do a lot of those. So that's kind of when you take a picture and you play with, like, TikTok, and you flip the page or expand the face, stuff like that. And if I look at number 20, here we have x, we have vector 1, vector 2, and we have the map from R2 to R2 be linear transformation, right? By the linear transformation is simply maps x into x1 v1 plus x2 v2. All right, looks familiar, right? Find matrix A such that Tx is Ax. So they want Tx to equal Ax. Well, let's see. If I take Tx equal x1 v1 plus x2 v2, that would be x1 times negative 2, 5 plus x2 times 7, negative 3. And wouldn't that simply be negative 2, 5, 7, negative 3? Do you remember we talked about that? So there's x. What's A? So A is simply negative 2, 7, 5, and negative 3. Like I said before, we should get used to the notation, moving forward and backward from this to this, so that when the time comes, we're very comfortable with this. And this is the official definition, something we're going to use lightly. Not to worry, we're not going to be doing a lot of proofs, but we're going to do some proofs, not a whole bunch. I know many teachers will get offended by what I just said, but it's all good. So the transformation, you have two options. A transformation is linear if you apply the transformation on the sum of two vectors and it turns out to be the sum of each, kind of like the algebra of functions. And if you multiply by a constant scalar, that turns out to be ineffective. You just take the scalar up front. This is an alternative. Instead of doing that, you could actually use this. Show that t of 0 equals 0, and if you take cu plus dv, you get them to be independent. So that's t applied on the sum is the sum of t's. And here's a problem, number 30, and it's asking the affine transformation has the form t operating on x is actually matrix A times x plus the vector b. Okay, they're saying show that t is not a linear transformation. I just want to really warn you, when b doesn't equal 0, I will never say show. I'll ask, is it? Is b a linear transformation? Well, if I take t, and again, the reason they're giving you this, it's a lot easier than the original definition. So this is what we're going to stick with. If I take t of 0, that is a times vector 0, right? And that would be, of course, the 0 vector, right? But it's not ax. If t of x was ax, that would have worked. We have a small minor exception here. That's b. What if b doesn't equal 0? Then t of 0 doesn't equal 0, which negate the first condition. And there's the homework for this section.